All right, so let us start our lecture today. In the previous class, we know that, okay, you have a function f, x, which is the sum a0 plus the sum when n is known from 1 to infinity of an cosinus of n pi x over L plus sinus of n pi x over L, right? So this happens when f is periodic, right? So f is periodic. Plus Bn. So this is Bn, right? So in the previous class, we know that if we have a periodic function, you can express that in terms of cosinus and sinus. All right? So now, in the previous class, we also know that if you want to take the second derivative of f, right, what you do is that this is going to be 0, and the other terms will be an n pi over L square cosinus, this is minus, of n pi x over L and then you're gonna plus that with Bn minus of n pi over L square of sinus of n pi x over L, right? All right, I explain again. So in the previous class, we know that if f is a periodic function with period 2L, you can express that in terms of the Fourier series. And if you want to take the second derivative of f, what you do is, okay, the first one is going to be 0. The other one, you want to multiply everything with a factor minus lambda n square over L, right? This is all what you have to do. You don't have to take the derivative. Instead, what you do is you multiply this factor to the Fourier series, right? This is because, so when we take the second derivative, we take the second derivative of a periodic function f, we multiply an and bn with minus n pi over L squared, right? This is what you need to do. You take the, you don't need to take the second derivative. What you do is that you multiply all of the coefficients out of the Fourier series with minus n pi over L squared, right? The reason is because so I call this factor lambda n. Lambda n is the eigenvalue, right, of the operator of the Laplace operator with periodic boundary condition. Right? So the reason that you can do that is because the Laplace operators has those factors as the eigenvalues, right? So you get what? You get cosinus of pi x over L. Second will be lambda n of cosinus of n pi x over L. Right? And then sinus of n pi x over L. Second is lambda n sinus of n pi x over L. Alright? Explain again. You have a Fourier series. The boundary condition here is very important. You need to have a periodic boundary condition in order to have a Fourier series. Alright? So, now if you take the second derivative, you don't have to do anything because what you have to do is you multiply all of the n and bn by this factor. This factor is called eigenvalue of the Laplace operator with periodic boundary condition because we are considering periodic functions. Alright? So the reason is, okay, cosinus n pi x over L. Second will be lambda n cosinus n pi x over L. And sinus of n pi x over L. Second will be lambda n sinus n pi x over L. Right? Now, there are two applications for this. The first application is the following. So suppose that we want we know that f second of x is cosinus of 1003 pi x over L. Right? And f is periodic, of course, f is periodic. F is periodic. Can we find f? Yes?
Sorry, for the eigenvalue, like the plus operator, so are you taking the second derivative of cosine and sine?
Mm-hmm.
So wouldn't those be wouldn't be negative?
So there's no negative because lambda n has a negative.
Okay, I got you.
Lambda n has a negative inside.
Okay.
Right?
Mm-hmm.
So here I have to multiply with the negative here as well. And the negative is inside the eigenvalue. Right? So application. Suppose that I know that there is a periodic function whose second derivative will be cosinus of n 103 pi x over L. How can I find f?
Do we have to put the entire derivative of f?
No,
I mean,
suppose that
right.
here I don't do an antiderivative. Anyone else? Yes?
Since f double prime x is equal to cosine, that whole thing there, we can reach that same result by multiplying with our transform.
Right.
So we can divide by.
Yes. Can you find at the back? Right? So you use this formula. You suppose that first f has this form because it has a Fourier transform. So the second derivative has to have this form. Now you identify this formula with that one, right? So what you do is you identify this formula with those so we know that f second of x will be the sum when n is going from 1 to infinity of an of lambda n cosinus of n pi x over L plus bn lambda n of sinus of n pi x over L. Right? This is the second derivative from here. Right? So this is lambda n and this is lambda n. Right? So you write out the first you write out a Fourier series of f, right? And the second derivative will be an bn lambda n sinus. I just want to remind you that here you have a0 per lambda 0, right? But lambda 0 is 0. Okay. Yes?
Would that be bn lambda n, not bn an?
Bn lambda n. Whoa, what?
Lambda in there looks a little bit like an a.
Yeah, I thought that was an a, sorry.
This is lambda. Right?
Okay, yeah.
This is lambda. Yes. Sorry. identify this with cosinus, right? Cosinus of 100 pi x over L. So can we find an and bn in this case? This is also in the hard questions in our exam, right? Suppose that I give you this function and I ask you to find the Fourier coefficient. How can I find it? In just one shot. I don't have to do computation. Yes?
It's going to be the same function cosine 1003 pi x divided by negative 1003 pi over L all squared, based on.
So I want to know what are the values of an and bn in this case?
Oh, okay.
Yes.
N going to be 1.
Bn should be 0 because lambda n can't be 0.
Yes, but I want to know everyone. Yes?
A would be 1 over lambda n.
No. So let us write this series out, and we're gonna see it. All right. So the f second, right? So if you ignore all of the sum, it's gonna be a1 lambda 1 cosinus of pi x over L, right? Plus b1 sinus of pi x over L. All right, plus a2 lambda 2 cosinus of pi 2x over L plus b2 sinus of 2 pi x over L. Plus a3 lambda 3 cosinus of 3 pi x over L plus b3 sinus of 3 pi x over L, right? And you take the sum until a 1003 lambda 103 cosinus of 1003 pi x over L plus b1003 lambda 1003 sinus of 1003 pi x over L, and you take the sum, you take the infinite sum, right? This is the meaning of this sum. I'm going to have a1 cosinus of pi x over L, b1 sinus pi x over L, and then cosinus 2 pi x over L, sinus 2 pi x over L, and at some point you're going to see cosinus 1003 pi x over L, and sinus 1003 pi x over L, and you continue this forever. Yes?
So would that suggest that everything but a sub 1003 lambda sub 1003 is equal to 0?
Right. So this means that this is the only thing which is not 0, right? This is the only thing which is not 0 because this guy is going to be this guy. And the other one, they're 0, right? So this is going to be 0 because you don't see it here. This is going to be 0. This is going to be 0. This is going to be 0. Everyone is 0 except this single term. See the point? Right? So if you expand it this way, so basically in the exam, what I gave you is a Fourier series. You don't have to do anything. You just pick up the term which is not 0, and you get the full point. So you identify the coefficient, right? So you have A113. This is bad. A1003 lambda 1003 is going to be 1. The other terms are 0. An will be 0 for n different from 1003, and bn will be 0 for n. Yes?
I know all the other terms are 0, but just like to make sense of it, the one after the box on the bottom, the b term, is the lambda supposed to be there on that one? Next
So
to
this
it?
is sinus, right?
No, but the one next to that. Like
This one?
it says d like 1003, and then like the lambda 1003, but it's not. There's like no lambda on the rest of the b's. Is it supposed to be like that?
So this, yes, there's lambda 1 here, yes.
So it is on the sheet.
Yes. Okay, can you say at the back of the paper, please? So we identify all of the coefficient and they should be lumped anyway, right? So basically, this is the midterm. I gave you a series. You just have to pick up the coefficient. That's it, right? So here you see that okay, in this series, you have the cosinus of 1,000 pi x over L, and there's only one guy like that here. So what you do is you pick this coefficient and you let it to be 1 and the other one there will be 0. Right? So now you're going to have what? You're going to have a 113 times will be 1 over lambda 113, and lambda 113 will be L over 113 pi squared. Alright? It's good? Yes?
What is the other boundary for Bn? Bn equals 0 for when n is what?
For all n. Right?
Oh, just any. Okay.
Yeah, so you look into this guy. Here you don't see that. So this should be 0.
Okay.
And this guy, yes?
Shouldn't it be negative L over 1003 pi?
Excellent. Can you say at the back of the paper? Yes, there's a minus here. Alright? So this is the only term which is different from 0. Now I'm going to look back into the formula. So the x will be a0, of course, because we haven't touched a0, it's always there, right? And then you're going to get a113 times cosinus of n pi x over L. Right? And a113 will be that guy, so f0 will be a minus of L over 113 square 113 of cosinus of 113 pi x over L. Alright? It's good? I explain again. Now, the power of this kind of thing is that you can take the derivative by multiplying all of the coefficients of the Fourier series with the eigenvalues. Yes?
Is it not negative L over 1003 pi?
Pi, yes. Can you say at the back of the paper, please? So the power of this is that you don't have to do derivative. You just have to multiply all of the coefficients with the eigenvalues. And then when you want to find functions whose second derivative is given, what you do is you identify the coefficients. For instance, in this case, f second is cosinus of 1003 pi over x over L. Alright, so I write down f second, which is all of those terms. You see that there is one guy. This one has the same form with this one, and the other term you don't see it here, right? So which means that this coefficient has to be 1, and everyone else has to be 0. So finally, you have an is 0 for n different from 003, and bn is 0 for n. So then you can compute 1003 by 1 over lambda over 1003, and this is the value of 1003. All right? So now you go back to f. But from this process, we don't see a0, right? So a0 can be anything. So you have to put back a0. And then the other terms will be 0, except this a1003. So I put it there, and the final answer is this one. It's good. Questions? It's clear? Yes?
How do we find out what A naught is?
A naught can be anything because you want to find a function whose second derivative is equal to this guy.
Okay.
Right? And when you take the second derivative, A naught will be 0, so A naught can be anything.
Okay.
So in this case, you have several solutions. You replace A naught by 1, 2, 3, 4, 5, you have a different solution. Right? Other questions? So basically, this is the key idea to solve partial differential equation, right? So you express the function in terms of all of the eigenvalues and the eigenfunction, and then you identify the coefficients. Now I have general strategy. Right, so given an operator, operator L, right? Suppose that the eigenvalues and eigenvectors are lambda n and phi n, right? Now, meaning that in this case, lambda L of lambda phi n is lambda n phi n, right? So in the previous case, the L is the second derivative. Lambda n is this L over minus n pi over L squared, right? And phi n will be either sinus or cosinus. Now suppose that U can be written like the sum when n is going from 0 to infinity of an times phi n, right?
What is the first?
The U. This is the function. So I'm gonna call it f. Right? Suppose that you can write f as the infinite sum of a and phi n. Right? So in this case, in order to compute LF, in order to compute LF, what you do is you multiply everything, all of the coefficients with an, lambda n, phi n, right?
From n is 0?
N is going from 0. The other one is going from n is going from 1 to infinity, but you can include 1, 0, because 0 is also an eigenvalue, right? So in the previous case, L is second of f with periodic, right? So I'm gonna emphasize a lot on this boundary condition because you can do Fourier transform only for periodic function, right? In the previous case, LF will be f second, right? Lambda 0 is 0, and phi 0 is going to be 1, right? Because you take the second derivative of 1, you're gonna get 0, right? So you have phi 0 second is going to be 0 times phi 0, right? In the previous case, 0 is also an eigenvalue because you take a constant, you take second derivative, you're gonna get 0, and this is 0 times 1, right? And phi n will be what? Lambda n will be minus of n pi over L squared, and phi n can be either cosinus of n pi x over L or sinus of n pi x over L. Right? So in the previous case, phi n, there are two values for phi n, either the cosinus or the sinus function, right? So when you take the second derivative of the cosinus, you get n pi over L squared cosinus minus. And then when you take the second derivative of the sinus function, you get minus of n pi over L squared sinus, right? So in this formula, I wrote only one phi n, but in the case that you have two phi n like that, you have to take all of the, you have to take all of the sum of them, right? It's clear? Now, the L of f will be L of f. L of f will be because the first one is 0, we can ignore that. So the L of f will be the lambda when n is going from 1 to infinity of lambda n a n pn. Right? So you don't have to do anything. You have to multiply all of the Fourier coefficient with the lambda n. Right? It's clear? I explain another time. All right? So if I give you an operator, so in the previous case, this operator is the second derivative, and I emphasize on the fact that the solution are periodic, because if you are not periodic, you cannot do Fourier transform, Fourier series. All right? Now, lambda n and Pn are called eigenvalues and eigenfunctions of the operator L if you have L of Pn is lambda n Pn. Now, if you can express this f is in terms of Pn, like this sum, or in the previous case, you have a Fourier series, right? So here I include A0 because 0 is also an eigenvalue for the second derivative. You take the second derivative of 1, you get 0. And then cosinus and sinus, they are eigenvalues as well, but but those eigenfunctions, but the eigenvalues of those functions are different from 0. So what you do is that whenever you take the action of this operator on L, you don't do anything, you just have to multiply all of the coefficient with the eigenvalues. And this is the key idea, how you can solve a partial differential equation, right? So now, how to solve? So how to solve? How to solve L of f is equal to g. So now in order to solve L of f is equal to g, what you do is that you rewrite g as the sum of n is going from 0 to infinity of Cn Pn. Right? In the previous case, we have only one terms, right? But in general, you have several terms, and what you do is you identify all of the coefficients. So suppose that you given g, you want to find f, right? So which means that given g, find f, right? Suppose that, for instance, in the previous case, we have f second is equal to cosinus. So, so given g, you want to find f. What you do is that you expand g in terms of all of the coefficients, right? And then you're gonna use this formula. So L of f will be somewhere n is going from 0 to infinity of an lambda n Pn, right? By this formula, you identify the coefficient. You're gonna identify Cn with an lambda n. So an lambda n will be equal to Cn, meaning that an will be Cn over lambda n. Right? It's good. So I explain again. So from the previous example, what we can see is the following. You can expand the function f. Suppose that you can expand the function f in terms of all of those eigenvalues, eigenfunctions, right? In the previous case, it was the Fourier series. So suppose that f is an Pn. So L of f is an times lambda n Pn, right? So in the previous case, we see that, okay, the second derivative of f will be an times this lambda n times cosinus and sinus, right? Now, if I give you a function g, and you have to solve f such that L of f is equal to g, what you do is that, okay, I'm gonna expand g in terms of all of those Pn, so g will be somewhere n is going from 0 to infinity of Cn Pn, right? And we know that L of f will be an lambda n Pn because of this formula, Now I identify the coefficient. Cn will be an lambda n, right? Right. This is what we did in the previous exercise. So now I have an lambda n is Cn, meaning that an is Cn over lambda n, right? So which means that f will be the sum when n is going from 0 to infinity of Cn over lambda n Pn. And this is how you solve partial differential equation. You have to find all of those lambda n, all of the eigenfunctions and eigenvalues, and then you just identify the coefficient. I expand this again once more. In the previous exercise, we have only one term, which is cosinus of 1003. So which means that we have C of 1003 is 1. But in this case, suppose that we have a lot of other terms. So I suppose I have Gn is the sum when n is going from 0 to infinity of Cn Pn. All right? So what you do is you write Lm, L of f. L of f will give you an lambda n Pn, right? Now, because L of f is equal to G, an lambda n has to equal to C, right? So now you can compute an by dividing by C, by dividing lambda n by C, right? So you replace an into the formula of this f, and then you have all of those coefficients of the function f. So you have the value of the function f that you need. It's clear? Questions? It's good? Right? So now, so far we have learned one case, which is the Fourier transform. Right? So for the Fourier transform, we know that the cosinus and sinus, their eigenvalues and eigenfunction of this second order operator, which is the second derivative, right? Now, question is that for other cases, when can we have eigenvalues and eigenfunction as well? So in the next step, we're gonna learn eigenvalues and eigenfunctions of differential operator. All right? Any questions on how on this framework? Yes.
What happens to L?
The L is the second derivative, right?
Yes.
So the L of f will give you this extra factor lambda in the coefficient, right? So L of f is a and lambda n Pn, because in the previous case you see that when you take the second derivative of the Fourier series, you gain a factor lambda n.
Yeah.
Right? So this is what happened to the L.
Okay.
Now, suppose that I give you a function g, and I say that L of f is equal to g. What should you do? You're gonna write g in terms of all of those eigenvalues and eigenfunctions. All right? And then you identify the coefficient.
Okay. Yeah.
Let me try to let us try to do another example, right? So that you understand this better. I want this. So let us try to do another example so that you understand better this idea before we go to the details of the next eigenvalue and eigenfunction begins. So right. So in the previous exercise we have the triangle wave, right? The triangle wave. So we have a function gx, which is equal to 1 plus x, when x is from -1 to 0, and 1 minus x when x is from 0 to 1. This is the triangle wave that we did in the previous exercise, right? Okay, so this is triangle wave. In the previous exercise, we know that this guy is a0 plus the sum when n is going from 1 to infinity of an cosinus of pi x plus bn sinus of n pi x. Right? In which a0 is 1/2 and an is 2 over n pi squared of 1 minus 1 to power n, and bn is 0. All right? It's good. Right. So this is what we computed in the previous exercise. We have a triangle wave, which is 1 plus x when x is from -1 to 0, and it is 1 minus x when x is going from 0 to 1. Right? Now, I want to find phi u such that u second is equal to 1 plus x when x is going from -1 to 0, and it's going to be 1 minus x when x is going from 0 to 1. Right? Now I want to solve the equation in which the second, I want to find a function such that the second derivative of this function is equal to the triangle wave. How do I do that? I do that, so in this case the operator L of u is going to be the second derivative. Right? And here you have periodic condition. Periodic. Right? The function has to be periodic, otherwise you cannot use Fourier series. But in the next step, we're going to learn other functions, other eigenvalues and eigenfunctions associated to functions which are not periodic. Right? So, but this is the easiest case. Let us do periodic. You want to find a function u such that u second is equal to the triangle wave. So how do I do that? Yes?
You set up a new function using the a to the n times lambda n times phi n is equal to the function that you're trying to get, and then solve for what cn would be.
Can you sign the background of paper, please? So this is a good idea, right? So first, you're gonna write u as the sum of the Fourier series. N is going from 1 to infinity of an cosinus of n pi x plus bn of sinus of n pi x. Right? First, you write u as in terms of a Fourier series. You don't know an, you don't know bn, you don't know a0, right? But you can write it this way. And what we want to do is we have to find a0, an, and bn. Right? So what I have to do is I I have to find a0, an, and bn, right? So what is the second derivative of u? Yes?
The Tran, right? So it's gonna be,
No, I'm not saying that. So what is the second derivative of this series?
oh, it's gonna be the sum from n to 1 to infinity of an times the eigenvector lambda n
Right.
cosine n by x plus bn.
Can you sign at the back of the paper, please? So the u second, right, will be the sum when n is going from 1 to infinity of an times the lambda n, right? Cosinus of n pi x plus bn lambda n sinus of n pi x. Sorry. Right? So you don't have to do the second derivative. You know that the second derivative will be all of the coefficients times the eigenvalue, right? So in this case, lambda n will be minus of n pi squared. All right? It's good. Now, you know that a u second will be of this form. So how can I compute capital A and capital B? Yes?
Would it just be like capital A-N is equal to lowercase a-n over
Lambda n.
lambda n?
Right. So here I put a0 to be 1/2, so there is no solution. So suppose that a0 is equal. So here I have 2 minus this final. So here is 1/2. Right. So a0 is 0. Sorry. Right. So in this case it's triangle wave, but with a 1/2. Right. So in this case you have what? You have an lambda n is going to be equal to this an. Right. This an and this bn is going to be equal to this bn. Right? So I have an lambda n is going to be equal to this an. And bn is going to be bn. Right? So this is how you do it. This is how you solve an equation. You just write down the expansion on the functions of that operator, right? So in this case, you have cosinus and sinus. So you write u as a Fourier series. You take a second derivative. You don't have to do anything. You multiply all of the coefficients with the eigenvalues. Now, you want to find this u, but the u second is already given here. So here you have all of the coefficients. A0 is 0, an is this guy, and bn is 0, right? So, which means that the an lambda n has to be equal to this small an, and the bn lambda n has to be equal to this small bn, right? Okay, so what is the capital Bn in this case? Yes?
Lowercase bn divided by lambda n.
Right. So in this case, can you sign at the back of the paper, please? So in this case, an will be small an dividing by lambda n, and this gives me this quantity, right? So this gives me 2 over, here I have a minus, so it's pi squared, 1 minus 1 to the n, right? And the bn will be 0. Because this small bn is 0, right? So now when I have the value for this capital An, what is the form for u? Yes?
Shouldn't be n pi to the
Can you sign the back of the paper, please? So here is a 4 power. because can you say? Right. So now, what is the form of the solution U? Yes.
So would it not be what we used previously? So U would be the sum from n equals 1 to infinity, and so the Cn over lambda n and Bn.
Yes.
So
Can you say the back of this? So I'm gonna use this an and I replace it here, and I replace Bn here. Right. A0 is not yet touched, so I have x will be A0. The Bn will be 0. So what I have is here is somewhere n is going from 1 to infinity of this guy. So I have minus 1 to the n minus 1 here divided by n pi to the power of 4. And then I have cosinus n pi x. And A0 can be any constant, right? Yes.
You forgot a 2.
The 2, yes. Can you say the vector please? Here I have a 2. Right? So basically this is the solution of that equation. It's clear? I explain again. So, the idea behind the eigenvalues and eigenfunctions is the following. You can take the derivative by multiplying all of the coefficients of the expansion with these eigenvalues, right? So in this case, you have, so here I have 1/2. In this case, I have the u second is equal to the triangle wave. And the Fourier expansion of the triangle waves, we already computed them in the previous exercise. So the triangle wave has the following form of the Fourier series, right? It's going to be A0 plus the sum when n is going from 1 to infinity of an cosinus n pi x plus bn sinus of n pi x. Bn is 0 and an is given by this formula, right? Now, I want to compute u second. I want to compute u such that u second is given by this Fourier transform, this Fourier series, right? So what I do is I write down u in terms of the Fourier series. I'm going to take the second derivative. So the second derivative of this series will be an times lambda n. I just have to multiply an with the coefficient and bn with the coefficient, right? And this is the form of u second. I identify the coefficient of this series with this series. So the A0 is going to be 0, is going to be fine. So the an is given by this one. So meaning that an lambda n is an, and bn lambda n is going to be this bn. Right? So this capital Bn will be 0 because this guy is 0. Now, an is given here, so you have an explicit form for the capital An. Right? So now you plug everything back into this formula, you get A0 plus the sum when n is going from 1 to infinity of 1 minus 1 to the n minus 1 n pi to the power 4 of cosinus n pi x. And the sinus is missing because Bn is 0. And this is the solution of the equation, right? So now you see the points of doing eigenvalues, right? So when you do eigenvalue, you just have to multiply all of the coefficient with this lambda n. So this is very simple. Yes?
So when we're solving like equations like this or problems like this, there's no way to find A0.
A0 is anything that can be. I mean, this is not that there's no way to find A0, but all A0 are fine for this. I mean, all A0 can be admissible to this series. See the point? So if I put 1 here, this is also one solution of this equation. If I put 10 here, this is also another solution of this equation, right? So you can choose A0, as you want, and this is still a solution of this equation, right? In this case, you don't have one solution, you have multiple solutions, right? Other questions? Yes?
Why did they change to 1/2 instead of 1 again?
Yes, I changed the 1/2 because I want this to be 0. If I put 1, here I have 1, so which means that here I don't have I0, but here I have I0, which means that I cannot find any u, just that u second is equal to the triangle wave. So in that case, you don't have solution, but I want to give you an equation where you have a solution, right? So if you put 1 here, the equation has no solution. Let me explain this point clearer. Now suppose that I go back to 1, right? Here I have 1/2, right? So here I have 1. Now, suppose that here I will replace 1/2 by 1. In this series, I have A0 is 1/2, which means that there is something at A0. I want the u second to be equal to this guy, but in the u second, there is no A0, which means that I cannot find any u, such that u second is equal to the triangle wave. In that case, you don't have solution, right? So if I replace this by 3, there's no solution. 1/2 is the only place where you have solution because it's going to give you 0 here. Questions? But that's a very good question. Can you sign the back of the paper, please? Other questions? All right. So now you see the point of doing all of the eigenvalues and eigenfunction. But this I emphasized several times that here the methods work only for periodic function because the Fourier series is specialized for periodic function, right? You cannot do functions that are not periodic using this method. So now we want to solve equations that involve functions which are not periodics. This is why we have to learn more functions, right? More functions that are not sinus and cosinus. So let us try to understand another case where we have right. So let us try to do so 2.3.6. So you find phi n and lambda n such that uxx phi n phi x phi second n is equal to lambda n phi n, and phi n at 0 is going to be 0, and phi n prime at 1 is going to be 0. Right? So from the previous exercise, from the previous Fourier series, we know that phi n is equal to lambda n phi n, and phi n is periodic on minus L to L, right? Meaning that you have what? You have lambda n, 0 is 1, and phi n is either cosinus of n pi x over L, and phi n is sinus of n pi x over L. Right? So this is what we need for a Fourier series. We consider periodic function. So for those periodic function, we look into cosinus and sinus function. Why? Because the second derivative of a cosinus function will give you lambda n times the cosinus function, and the second derivative of the sinus function will give you lambda n times the sinus function. It's clear? So this is what we wrote in the previous case. You have 1 is equal to 0 times 1, and cosinus of n pi x over L. To the second will be minus of n pi over L squared. Cosinus of n pi x over L. Sinus of n pi x over L second will give you minus n pi over L squared. Right? So the cosinus and sinus, those functions are used in the Fourier series, have a very nice property, which is the following. So those functions are periodic, and those functions satisfy the fact that the second derivative of cosinus is going to give you lambda n times cosinus, or sinus, second derivative will give you lambda n times sinus. All right? So the cosinus and sinus are called eigenfunctions of this operator with periodic boundary condition, right? So those are used for periodic function. But I want to study functions that are not just periodic. This is why I have to consider other cases. And another thing that is so limited for the Fourier series is the fact that you have to be symmetric, right? Remember that if you want to do something which is not symmetric, you have to shift it back to the origin. Now, suppose that I want to study functions that are not periodic, right? So I want to try. I want to find functions that have similar properties like that, but the boundary condition is different, right? The x is now from 0 to 1. And I'm going to look for phi n such that phi n second is lambda n phi n on 0 to 1, right? In this case, the interval is 0 to 1 and not minus 1 to 1. So this interval is not symmetric, right? And the boundary condition is not periodic. So I want to find phi n such that phi 0 is equal to 0 at 0, and phi prime at 1 is equal to 0. So I want to search for those functions to see the difference between those functions and the cosinus and sinus. And if I'm lucky enough, I can create a new basis to replace the Fourier series. See the point? So I explain again. So the point of the Fourier series is the fact that you are on a symmetric domain from minus L to L, right? So in the Fourier series, you use the function 1, cosinus and sinus, because when you take the second derivative of cosinus, you get back cosinus with a factor which is lambda n. So the cosinus and sinus are called eigenfunctions. And the lambda n, which is minus n pi over L squared, is called eigenvalue, right? So this Fourier series is for periodic function. Now I want to find similar function on intervals that are not symmetric with different boundary condition, right? In this case, in this example, I want to find a function such that the second derivative of phi n, a class of function, such that the second derivative of phi n is going to be lambda n phi n. So those functions are similar to cosinus and sinus, but the boundary conditions are different. I want phi n at 0 to be 0 and phi n at 1 to be 0, right? So let's try to find those functions. Any questions? So you see the transition between Fourier series and the new the new problem, right? So the transition is that, okay, I want to move from periodic boundary condition to general boundary condition, but still keep this nice property that you have second derivative is lambda n phi n. All right, so now let us try to solve this equation. Solution. All right. So how can I solve this differential equation? This is what? Solution. Phi n second is lambda n phi n. So this is the second order differential equation, right? How do I solve a second order differential equation with constant coefficient? And this equation is homogeneous, right? So you have minus, and this is 0. This is one of, yes?
We have to do the superposition principle where we have to solve for the homogeneous and the particulate.
No, no. This is exercise 4 in the homework one. So this is the pretest, right? So in the beginning of the class, I gave you a second order differential equation and I asked you to solve it, right? Remember that in one of the exam exercise, we have something like this. Remember that? Or minus or something, I don't remember. Right? So how can I solve a second order differential equation? Yes?
Find the root.
You find it, yes. You write down the characteristic equation and then you find the roots, right? So the characteristic equation will be x squared minus lambda n is equal to 0, right? It's clear, right? So I remind you that, okay? I remind you that, okay, suppose that you want to solve u second minus 9u is 0. What you do is you write down the characteristic equation, which is x squared minus 9 is equal to 0, right? And you find two solutions. The first one is 3, and the second one is minus 3, right? So the solution will be the linear combination of the two. E to the 3t, c1 plus c2 e to the power minus 3t. All right? This is how you solve second order linear differential equation with constant coefficient, right? So now, so if you don't remember how to solve it, you just go back to the first homework, which is the pretest, and in the pretest, in the solution of the pretest that I posted online, you have a solution, right? And this is from 3313, which is a 3000 level class, introduction to this. So now let us look at this equation. X squared minus lambda is going to be 0, right? Right. So how many cases should I consider? No. One is not good, 2 is not good. How many is good?
8 billion.
No. 3. Who said 3? Yes, can you say at the back of the paper, please? There are 3 cases, right? So if you look into a characteristic equation of a second order differential equation with constant coefficient, you have a quadratic form. So there are 3 cases. If the quadratic form has 2 real solutions, if the quadratic form has 2 complex solutions, and if the quadratic form has a double solution, right? So now we consider case number 1. Lambda n is strictly greater than 0. So if lambda n is strictly greater than 0, what are the solutions of x? Can you say at the back of the paper, please? So when lambda n is strictly greater than 0, you have what? You have x1 is the square root of lambda n, and x2 is minus the square root of lambda n. Right? So what are the 2 solutions of this differential equation? Yes?
Plus or minus root lambda n.
No, of the differential equation.
No.
Constant 1 e to the root lambda n plus constant 2 e to the root lambda, negative lambda n.
Yes?
It's that we're missing a cosine and sine term. It would be the.
No. The cosine and sine is the third case,
Oh,
the complex case. Right?
Root
So
lambda n, root lambda n x
yes. Can you say
plus
the
c2
magnitude of this?
e to the root negative.
Right. So you have 2 solutions, right? E to the lambda n t and e to the power minus lambda n t. Right. So if this is a second order differential equation with constant coefficient. So if you want to solve it, you look into the characteristic equation. Now, if lambda n is strictly positive, the characteristic equation has two solutions. Square root of lambda n or minus square root of lambda n. And this gives you two solutions for this differential equation, which is the exponential of those roots, right? So now the phi n will be the linear combination of these two roots, right? All right. Now we have a general solution, and C1 and C2 are constant. So what is the next step? Yes?
You have to, you have to solve for C1 and C2 by plugging in the boundary values.
Can you say at the back of the paper, please? So now we're gonna use the boundary condition, right? So you have what? You have phi n and 0 is going to be 0. All right? So I'm gonna replace 0 here. I have C1 e to the power square root of lambda n times 0 plus C2 e to the power minus lambda n times 0. And this is going to be 0, meaning that C1 plus C2 is going to be 0. Right? It's good. Next step. Yes?
Take another
Barry.
condition.
Can you stand at the back of the paper, please? Now I'm going to use the second condition, right? So I have phi n at 1 is going to be 0. So here I have C1 is plus C2 is going to be 0, so C2 is minus C1. All right? In this case, I have C2 is minus C1, so phi n will be C1 e to the square root of lambda n t minus C1 e to the power square root of lambda n t. All right? Now I'm gonna use the second boundary condition, right? So phi n prime at 1 is going to be 0. So phi n prime at t will be, what is phi n prime at t? Yes?
It would be C1 times root lambda n e to the root lambda n t minus C1 root lambda, or plus C1 root lambda n t and times e negative, there's a lot.
Yes, can you stand the back of the paper, please? So then you're going to have C1 square root lambda n e to the power minus lambda n t. Right? This is the derivative. So after the first boundary condition, I replace C2 to be minus C1. So I have C1 is square root lambda n minus C1 e to power minus square root lambda n t. I take the derivative, this gives me this guy. So I'm gonna use the fact that phi1 is going to be 0, meaning that you have C1 square root lambda n e to square root lambda n times 1 plus e to the square root lambda n times 1. All right? Yes?
Why isn't the second part of the term negative C2? Because aren't you bringing out the negative when you're doing the changing of the derivative? Right? The negative C2 lambda.
Yeah.
Or on the lambda n prime t, shouldn't that is that not negative C2 in that case? Negative C2 lambda n?
This is C1, right? So C2 is minus C1.
Oh, okay.
Right, so I replace this here, right? So I replace C2 by minus C1, all right? So here I have C1 square root of lambda n is square root of lambda n t plus C1 square root of lambda n e to power minus square root of lambda n t, right? Because here I replace it already here. So from this equation, what can I say about C1?
It's
0.
0.
Can you say at the back of the paper, please? So C1 is 0, or square root of lambda n is 0, right? So this one is always positive. It's exponential plus exponential. Exponential is never 0, right? So this guy is strictly positive, meaning that C1 is 0, on square root lambda n is 0, right? So if C1 is 0, you replace it here. So phi n t is also 0, right? So phi n t is 0. So if lambda n is 0, then phi n is also 0, right? So in this case, you have a 0 eigen values and 0 eigen functions, right? So in this case, phi n is 0. Phi n is 0. So lambda n is also 0, right? So you have 0 eigenvalues and 0 eigenfunctions. Explain again. Right. So the difference between this problem and the sinus and cosinus problem is that you are considering the same eigenvalues thing, but on an interval from 0 to 1, not from minus L to L. So this interval is not symmetric, and the boundary conditions is different. So here you don't have periodic functions, you have something else. But let's try to find those phi n and lambda n that satisfy this system, so that later on we can do something with it, right? Now, you have what? You have phi second minus lambda n is 0. So we know that from the previous class, so this is something that you need to know. So this is also mentioned in the first homework. In the case that you don't remember this, I recommend you to read again the material of 3313, which is Introduction to the Differential Equation. So in order to solve a second order differential equation, homogeneous with constant coefficient, what you do is you look into the characteristic equation, which is x squared minus lambda n. There are three cases. The first case is lambda n is strictly positive. When lambda n is strictly positive, you have two distinct solutions, square root lambda n or minus square root lambda n. All right? So this gives you two solutions, and you have to linearly combine them. So phi n t will be c1 e to square root of lambda n t plus c2 e to square root minus lambda n t, right? And you want to find c1 and c2. You find c1 and c2 using those boundary conditions. So phi0 is 0, meaning that, okay, c1 exponential of this guy plus c2 exponential of this guy is 0. This and this, they're both 1, so you have c1 plus c2 is 0. c2 is then minus c1. You replace c2 back into this form, so phi n t will be c1 is square root of lambda n t minus c1 of this e to power minus square root lambda n t, right? Now you use the second boundary condition, phi n prime of 1 is 0. So phi n of t, I take the derivative of this guy, I get this form. So I replace 1, I get 0 is c1 square root of lambda n exponential plus exponential. So this is exponential, this has to be positive, and this is also positive, right? Exponential has to be positive. So this guy has to be positive, so I can remove it. So I have c1 is 0, or square root of lambda n is 0. So if c1 is 0, I use this formula, phi n is 0. So if lambda n is 0, again, I use this formula and phi n is also 0, yes?
If root lambda n is equal to 0, I don't see how phi n would be 0, because you have e to the 0, which is 1. So
Right.
what if phi n be c1 minus?
So this is c1, 1, right?
Yeah.
This is c1. This is c1, 1. This is c1. This one minus
Right.
this one, 0. So in both cases, you have phi n is 0, and lambda n has to be 0. This contradicts the fact that you have lambda n is positive. Right? So contradiction. Right? Questions? Now, the second case. Any questions on the first case? You're gonna get three cases. The first case is always so in the first case you will not find anything in the first case. What you want to find is in the second case and the first case. Alright? Now, case number 2. What is case number 2? Yes?
Lambda equals zero.
Yes, can you sign the back of the paper, please? So case number 2, lambda is 0. So what happened when lambda is 0? You will not be able to find anything in the first case, but you always have to consider the first case. Now the second case, if lambda is 0, what happened? Yes?
You have one solution.
Yes. Can you sign the back of the paper, please? So when lambda is 0, right? So this and second will be 0. Right? So what is the solution for Vn?
Zero.
No. No. Phi second is 0. What is phi?
Yeah, a constant times the original function of t. Right? So like, because if you integrate it,
Do we
you
any constant?
No. So this is something that we consider already, right? So this is it plus b. Right? We're gonna continue this on Thursday.